Hello students. It's great to have you here again. Today, we're diving into part 1 of electric fields. But before we jump in, let's quickly review what we covered in our last lesson. In our last class, we discussed natural satellites, such as the moon, and artificial satellites, which are also known as man-made satellites. We also explored the concept of escape velocity, which is the minimum speed required to launch a satellite into space. Today's goal is to explore the concept of sources of charges and electric circuits. An electric field is the region around a charged object where other charged bodies experience an electric force. In electricity, charges refer to the property of matter that causes it to experience a force when placed in an electric field. Electric charges are of two types: positive charges, which are carried by particles like protons, and negative charges, which are carried by electrons. There are two types of electrochemical cells. Primary cell. These are non-rechargeable sources of electrical energy. Once the chemicals are used up, the cell cannot be reused. They are cheap and easy to use. Example: dry cell, Leclanche cell, which are battery cells commonly used in devices like remote controls and flashlights to provide portable power. While secondary cell are rechargeable sources of electrical energy. Once the chemicals are used up, the cell can be recharged. They are more expensive and last longer. Example: lead acid accumulator, lithium-ion battery. They are the battery in your smartphone and car battery. You're making progress, keep it up. Electric circuits can be arranged in two main ways: series and parallel. In a series arrangement, the components are connected end-to-end in a single path, so the same current flows through each component. The total resistance in a series circuit is the sum of the individual resistances of all components. In a series circuit, resistors are connected one after another, like links in a chain. The electric current has only one path to follow, so every component shares the same current. Here is the formula: the total resistance in a series circuit is the sum of all individual resistances. So, if you add more resistors, the total resistance increases, just like adding more blocks to a wall. Remember, in a series circuit, adding more resistors increases the total resistance. Also, on parallel arrangement of circuit, the components are connected across the same 2 points, creating multiple paths for current to flow. In this setup, the voltage is the same across each component. However, the total resistance is calculated differently. It is found by taking the reciprocal of the sum of the reciprocals of the individual resistances. In a parallel circuit, resistors are connected side by side, across the same 2 points, like lanes on a highway. This allows the electric current to split and flow through multiple paths at once. In a parallel setup, something interesting happens. The total resistance actually decreases as you add more resistors. In other words, R total equals 1 divided by the sum of 1 over R1, 1 over R2, 1 over R3, and so on. Think of it this way: adding more lanes to a road lets traffic move more freely. In the same way, adding more paths in a parallel circuit makes it easier for current to flow. So, in a parallel circuit, adding more resistors decreases the overall resistance. I know this might be tricky, but stick with me. Let's solve an example. A circuit contains 3 resistors. R1 is equal to 4 ohms. R2 is equal to 6 ohms. R3 is equal to 12 ohms. A. What is the total resistance if the resistors are connected in series? B. What is the total resistance if the resistors are connected in parallel? Let's solve a simple resistor problem using both series and parallel connections. We have 3 resistors. R1 is 4 ohms, R2 is 6 ohms, and R3 is 12 ohms. Now, let's calculate the total resistance in 2 ways. First, when they are connected in series. In a series connection, resistors are added directly. So, the total resistance is R total equals R1 plus R2 plus R3. That's 4 plus 6 plus 12, which equals 22 ohms. So, the total resistance in series is 22 ohms. Now, let's find the total resistance when the resistors are connected in parallel. We use the formula 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. Substituting the values gives us 1 over 4 plus 1 over 6 plus 1 over 12. We need to find a common denominator, the smallest number all three denominators can divide into. The least common denominator of 4, 6, and 12 is 12. We now rewrite each fraction so the denominator is 12. Multiplying the numerator and the denominator of the first fraction by 3 gives us 3 over 12. Multiplying the numerator and the denominator of the second fraction by 2 gives us 2 over 12. Multiplying the numerator and the denominator of the third fraction by 1 gives us 1 over 12. Adding the fractions. 3 over 12 plus 2 over 12 plus 1 over 12 equals 6 over 12. That is 3 plus 2 plus 1 all over 12 equals 6 over 12. So 6 over 12 simplifies to 1 over 2. So 1 over R total is 1 over 2, then we cross multiply, and that means R total equals 2 ohms. Therefore, the total resistance in parallel is 2 ohms. Remember, in a series circuit, resistances add up, but in a parallel circuit, the total resistance becomes smaller. Congratulations! You've come to the end of this lesson. Put your knowledge to the test by trying these questions. They are a great way to deepen your understanding. We've covered sources of charges and electric circuits in today's session. I hope you found the class both engaging and informative. In our next lesson, we'll continue our exploration in electric field, part 2. Thank you.